Last video, we saw the cycle notation as a way of breaking down an arbitrary permutation into relatively simple building blocks. In this video, we ask a sort of follow-up question, which is, are there any simpler building blocks? Can I break anything down further? And the answer is yes and no. It's yes in the following sense. Let's say that you are at I don't know, you ever be at one of those fairs or like you see a street game where there's like cups and then someone like mixes up the cups and you have to guess like where a marble is or something. I mean if it's a marble you'd hear it, but I think you guys know the game I'm talking about, where things are like randomized in some sense and then you have to figure out like where something is. Notice that when you're doing that kind of randomization like with your literal hands, you're taking like two cups at a time and like switching them in some way. So if you have some, I don't know, here's a randomization of 5 cups. We're going to pretend these are cups. You could think about like how these got here in terms of undoing it, right? Like the process that gets you from the original ordered sequence 1, 2, 3, 4, 5 to this sequence is a way of shuffling. And so we can undo that using what are called transpositions. Transposition means you take two things and you just switch them. And we know that that has to be possible because that's how they get shuffled up, right? So for example, I could switch 1 and 3 to put 1 into place. And then I could switch 3 and 4 and get these into place. And so what we're seeing is it with two switches, I can get from the original shuffle ordered sequence to the shuffled sequence. And I don't think that that's like super visible from the start. I mean, when I look at 3, 2, 4, 1, 5, I don't have an immediate sense of like how hard it would be to reach that permutation using just these interweavings of two things at a time. And so in this way, we can always break down any cycle into transpositions. I'll give you a couple examples. Here's in cycle notation a 5 cycle. This can be factored into transpositions, and I'll show you there are two ways that I can think of that are obvious. Well, obvious to me with my experience of doing a lot of algebra. That looks like this. And there's at least one more factorization that uses the same idea, but kind of goes in the opposite order. So I should write it like so. And I'm going to let you guys take a moment and pause the video and actually check that when you calculate this through, right, when you work out what happens to 1, you see that 1 goes to 2 and 2 goes to 3 and so on. And I'll give you a hint if you feel a little bit stuck. In each case, the repeated symbol 1 functions a little bit like a handoff gadget that links each of these transpositions to the next one. All right, I'm going to assume, as I've been yapping, pause there for a moment, that you did that, and now you're convinced. I'll show you at least one more factorization that's not so obvious, and then we can verify that. This factorization starts the same as the first one does, but then we insert a little, I don't know what you call this. Sorry, this isn't even going to work. This isn't right. Hold on. Let me think for a minute. I think having the 5-1 is fine, but what I need is, I think like this, because this would, okay, you know what? I'm not going to try to think it out loud. Let's just check, right? If it works, it works. So if I start with 1 here, 1 goes to 4 by this guy, 4 goes back to 1 by this guy, and then this 1 is handed off to this 5, and then this 5 goes to this 3. So something's not right here. So this did not work exactly as written because I need this to be a 2 if it's going to go where I think it needs to go. So maybe this is how it goes. 1 goes to 4, 4 goes back to 1. 1 goes to 5, 5 goes to 2. That part is right. Now it's matching. 2 goes to 3, and then 3 appears nowhere else in the list. So we get to 3. I think now it's going to work. 3 goes to 2, 2 goes to 5, 5 goes to 4, 4 goes to 1, 1 goes to 4, 4 goes to 5. It worked. Okay, good. We got it. A little bit of trial and error there. Sorry about that. That's my bad. But this, in fact, works. And so this is the no side. So there was a yes side to can you factor it further into transpositions? You always can factor things into transpositions. But the no side is that you cannot do this in a unique way. Factorization into transpositions is not unique. And what we're seeing is it's not even close to unique because you have these guys here, which are the same length, but then this one, which has got 2 more. So this is length 4, right? This is length 4. This is length 6. And it turns out that this is the best you can do. So this is going to be our theorem for the video. Any factorization into transpositions has the same parity. That's what parity refers to, oddness or evenness. So in other words, if you factor this into transpositions, no matter how you do it, since this one is 4, you're always going to get an even number. It could be like pretty much any even number. Well, okay, it can't be 2. You can check that you need more than 2 swaps, right? You can see kind of here. You need more than 2 swaps to get to this, but it could be 4, it could be 6, it could be 26. It's always going to be an even number, but that's really all you can say. And in some sense, hopefully that makes at least a little bit of intuitive sense, because in light of our discussion from last time, we know that every transposition is its own inverse because it's a 2 cycle. So if I have like 2, 3, and then another 2, 3, those are going to multiply to the identity. And so I could always stick things like this in here that are going to just cancel out in a sneaky kind of way. And I think if you look carefully at these, you will be able to convince yourself that that's exactly kind of what happened here. Is this was snuck in as like a sneaky way to insert a useless transposition, right? This 1, 4 and 3, 2, right? These are disjoint cycles, they commute. So we could switch them, cancel them, and then have something else of length 4. In any case, let's focus on proving this theorem now that we have some intuition. So first we have a little lemma. Lemma is a math term for when you have a useful step in a theorem that's important of its own accord, but it's less than the full theorem. And the lemma says the identity permutation right, the neutral element, always factors as an even number of transpositions. Not mutations, transpositions. Words. Okay, so what we're going to do to prove this little lemma is work systematically through the possibilities. Let me show you how that might look. So we start by writing down our identity permutation as a product of some transpositions, which we'll call T's. So this is some big product here. What I will do, we will show that transpositions are always eliminated in pairs, and that you always can do some elimination. What this will do together is allow me to knock 2 of these off at a time until I either run out, in which case there were an even number originally, or if I didn't run out somehow, that would mean that we would end up with some epsilon, sorry, the neutral element, the epsilon, equals some transposition, which I don't know, I'll call it T star, because it doesn't matter like what kind of transposition it is. But this is clearly ridiculous, right? Because the guy on the left is the neutral element, which does nothing. This is doing something. It's switching something. So this doesn't happen. So in other words, if I show that I knock them off two at a time and that I always can do it, it must be the case that they appear in pairs. So here's how we go about doing this. Towards the always can do some elimination part, we are going to look for two possibilities here. First, we let x be some symbol appearing among the t's, right? It's some symbol being mixed up in that big hodgepodge of transpositions. What we do is we will either seek to move x to the left or eliminate x. The reason for doing this is because if there's only one x in this whole thing, then we can't possibly do anything with it, right? That sounds like we're headed towards the case that was impossible. Otherwise, what we're going to try to do is take the x's and bring them together, right? We don't know where in this big ugly mess they may be, but if I'm always trying to move the x's to the left, then eventually they'll come side by side, and then we'll be able to do some kind of calculation, and maybe it'll get removed, and maybe that'll be the pair that we eliminate. That's kind of the idea here. I understand it's a little bit vague, and maybe we don't fully believe that it'll work. So let's try to think through a little bit closer what it means exactly. Since x appears among the t's, let's suppose that the last time it appears, that's left to right, is tk. And then we write this transposition as xa, right? A is just some other symbol being mixed up. There are 4 cases oops, sorry about that. For what tk minus 1 looks like. Let's write down the 4 cases. So the first case is tk minus 1 is also equal to xa. They're just exactly the same. Case 2, we have another cycle, another transposition involving x, but it's doing something with it's getting swapped with something different than just a, so maybe it's b. Case 3 is that tk minus 1 is swapping something with a, but it's not x. And then the fourth case is whatever it is, it's just some entirely irrelevant cycle. So, first things first, if they're xa, if tk minus 1 is also xa, then tk minus 1 tk is just 2 xa's that are side by side, and so we cancel. See, I eliminated 2 things. They disappeared in pairs. In case 2, if I have xb xa, right, tk minus 1 times tk, like so, then what I want you to observe is that this can be rewritten as xa ab. It's worth it to take a moment and pause the video and convince yourself that that is correct, because, well, I don't think it's super crystal clear, but it's true. This has the effect of moving the last presence of x went left, right? It used to be the last x was in the tk slot. Now the last x is in the tk minus 1 slot. And so even though we did not cancel anything, we succeeded in moving x to the left, which is one of the goals that we had, right? We could move x to the left or we could eliminate x. In case 3, we have CA XA as a possibility. And again, it's worth it to like pause the video here and verify that what I'm saying is correct. But this product of transpositions can be written as XC CA. And we moved the last x to the left. Oops, sorry about that. The last one is the most boring because here, if I have BC XA, these are disjoint cycles, so I can just switch them. And the last x to the left. So by doing this process over and over and over again, we loop the process until x's come together and drop out. And when they drop out in pairs. And so in this way, we are streamlining the calculation over and over and over again until everything is gone and we're done. Since they dropped out in pairs, it's even. At this point in time, we are most of the way to the end here, right? I've proven the lemma. Now let's see that the lemma implies the theorem. Suppose some permutation, let's call that permutation, I don't know, sigma, can be factored into two different collections of transpositions with opposite parity, right? In other words, one is odd and one is even. Well, then what that would tell me is if I call one of those big product thingies alpha, I don't know how to explain this. Well, hold on, let me think for a second. If sigma is factored into two different ways, then sigma inverse is obtained by reversing the order of all the transpositions. Why? Because with the shoes and socks lemma, right? Shoes and socks lemma says when you invert a product, you have to flip the order around and make everything inverse. But every transposition is just its own inverse. So all you got to do is write the transpositions in the opposite order. So let's say then that we have two such factorizations. I take one of them and I reverse the order. That's sigma inverse. Because all I did is reverse the order, it's got the same number of terms in it as the original sigma. So that means sigma inverse, maybe that's the odd one, times sigma, and that's the even one. So this has an odd number of terms. This has an even number of terms. It doesn't really matter which one is which. You could switch them if you want to. This is the identity element, though, right? Because these things obviously cancel out. And moreover, when I multiply them, the length of the thing is an odd number plus an even number. So that would mean that I wrote the identity as a bunch of as an odd collection of transpositions. But the lemma says that's impossible. So therefore, one of these two things is wrong. It has to be the other one, but there is only two possibilities. So if the odd one is wrong, they're both even. If the even one is wrong, they're both odd. And odd plus odd makes even. And so we're happy.